Moving on to problem 4.31. Construct a 16:1 multiplexer with two 8:1 and one 2:1 multiplexer. Solution for this is a 16:1 multiplexer has four select lines, and depending on the voltage levels or the logic levels at the select lines, it will select the data at one of the inputs and give that as the output. So in a 16:1 multiplexer, there are four select lines, 16 input lines, and one output line. Suppose we have two 8:1 multiplexers. In parallel in the first stage. That's an 8:1 mux. That is also an 8:1 mux. And then we select either the top mux or the bottom mux depending on some control input and give that as the output. So suppose the select lines are, since there are four select lines, S3, S2, S1, S0. I'll give S3 here, S2, S1 and S0 here, S2, S1 and S0 here. So since, as we have seen in the truth table in one of the earlier questions, the first half of the input combinations differ from the second half of the input combinations, the entire set, only in the most significant bit. So 0 0 0 0 0 0 represents 0, and a 1 in the MSB, 0 followed by three zeros represents a 0. A 1 followed by three zeros represents an 8. Similarly, 0 0 1, if it's preceded by a 0, it's a 1. If it's preceded by a 1, it's a 9. That is 8 more than 1. So if the values of the last three bits are the same, then if the most significant bit is 0, then the most significant bit is 1, then it is 8 more than the value you would have if the most significant bit was 0. Because obviously this is the 8th position. If you if it's a binary number, this is 8421. This is the 8th position, so if that is 1, an 8 is added to the number. So using that, what do we want in a 16:1 multiplexer? There are 16 inputs, and if the input is 0000, we want to select I0. If it is 1000, we want to select I8. So this circuit that I have drawn here does exactly the same. These are S2, S1, S0, and this is S3. Both these combinations, S2, S1, S0 is 000, so it's selecting the first output among the 8 both multiplexers, and then depending on whether S3 is 0 or 1, it will select the top mux or the bottom mux. So if S3 is 0, then you are supposed to select I0. So since S3 is 0, it will select this output, which is I0 now, and this is I8. If S3 is 1, I8 will be selected and fed as output. So in this way you can get a larger sized multiplexer using smaller size multiplexers. And by size I mean the size of the number of inputs and the number of outputs and the number of select lines. Problem 4.32. Implement the following Boolean function with a multiplexer. The function is f of abcd is summation 0 to 5 8 10 14. And part B is f of abcd is product of 2 6 and 11. There are different ways to do this. The way I would do it, well, of course, practical considerations are right. Theoretically, if you want to solve it, you could do it in different ways. The way I would do it is, since I have not mentioned what the size of the multiplexer is, I will take the 16:1 multiplexer from the previous problem. That will have 4 select lines. I'll give ABCD as the 4 select lines. So if ABCD is 0, it will select the first select line. And I want the function to be high whenever ABCD is 0, 2, 5, 8, 10 or 14. So to the 0th input, the second input, 5th, to draw a bigger diagram. There need to be 16 inputs, and the control select lines will be ABCD, and 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14 will be ones, and the rest will be zeros. And this will implement f of ABCD. In part B, we have f is pi of 2611. Which can be further written sum of minterms, and those minterms those minterms with indices that are not present in the products form. So other than 2, 6, 11, you have to include all the other minterms: 7, 8, 9, 10, 12, 13, 14, 15. It's the same logic, except the ones and zeros will be different now. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That will implement the desired circuit. Problem 4.33: implement a full adder with two 4:1 multiplexers. A full adder has three inputs A, B, and carry in, and the two outputs. First output is S, which is A XOR B XOR C in. Right, instead of using the Boolean expression directly, let us Write down the truth table. Let the input numbers be ABC and output be the sum and carry. 0 0 0 sum is 0, carry is 0. 0 0 1 sum is 1, carry is 0. 0 1 0 sum is 1, carry is 0. 0 1 1 sum is 0, carry is 1. 1 0 0 1 and 0. 1 0 1 0 and 1. 1 1 0 0 and 1. 1 1 1 1 and 1. Now one way to use a 4:1 multiplexer has two select lines. So we can use two of these inputs as select lines S2 and S1 and S0. When you do that, you can see that S1 S0 are 0 0 for these two combinations. S1 S0 are 0 1 for these two combinations. S1 S0 is 1 0 for those two combinations, and S1 S0 is 1 1 for the last two combinations. And from this you can see that the first two combinations, the sum is the same as the carry in. So carry in is 0, sum is 0, carry in is 1, sum is 1. In the next two combinations, the sum is the complement of carry in. In the next two, it's again complement. In the final one, it's just carry in itself. And in the first two input combinations, the carry is just 0. In the last two, it's just 1. In these two input combinations, the carry is simply C in itself, and here it's the complement of C in. So what you now do is you use one 4:1 multiplexer for your sum, the other 4:1 multiplexer for your carry. The select lines are two of the inputs, A and B. Now the first multiplexer gives you the sum. So in A and B are 0 0, you need to get C in as your sum. So you give this to C in. When A and B are 1 1 also, you get C in as the sum. So you give both of them to C in. And when AB are 1 0 or 0 1, when it is 1 0 1, you select I1, and 1 0, you will select I2. In both those cases, you give the complement of Cn, and that will give you the sum. Similarly, for the carry, when ABR 0 0, carry will be 0 regardless of value of Cn, and when A and B are 1 1, carry will be 1 regardless of the value of Cn, and when A and B are 0 0 1, the carry is Cn, and when A and B are 1 0, carry out is carry in complement. So this is the way you can implement a full adder using two 4:1 multiplexers. But practically this is useless unless, of course, you don't have gates directly. You have only multiplexers. Then you will need to get your full adders in this way. But if you can directly use gates, you'll need way fewer gates to get your sum and carry. Because you need one OR gate and four AND gates to make a 4:1 mux. So in total, if you have two 4:1 muxes, you'll need, excluding the NOT gates, 8 AND gates and 2 OR gates. But a full adder probably takes fewer gates than that. Anyway, we'll move on to the next problem. Problem 4.34. An 8:1 multiplexer has inputs A, B, and C connected to the select inputs S2, S1, and S0 respectively. The data inputs I0 through I7 are as follows. In the first part, I1, I2, I7 are 0, I3, I5 are 1, I0, I4 are equal to D, and I6 is D prime. In part B, you have I1, I2 is 0, I3, I7 are 1, I4, I5 are D, I0, I6 are D prime. Let's look at the solution. The function is a prime b prime c prime I0 plus a prime b prime c I1 plus etc. up to a b c I7. That if you substitute the values for I0 I to I7, you get f is a prime b prime c prime goes to 0 since I0 is 0, a prime b c prime is ANDed with 0 and ABC is ANDed with 0. So those terms won't show up. I3 and I5 will show up. So I3 is, you have A prime BC into I3. Since I3 is 1, you have A prime BC. And you have AB prime C into I5. Since I5 is 1, you have AB prime C. Then you have A prime B prime C prime D, because I0 is D, and A prime B prime A prime B, sorry, A B prime C prime I4, and I4 is D, so A B prime C prime D plus I6 A B C prime I6, which is A B C prime D prime. That is the Boolean function. Of course, you could simplify this further using K-map. The question doesn't ask us to give the Boolean expression in any particular form, so we can leave it at that. Similarly, for the second part, f has I3 A prime BC, I7 ABC, I4 is A B prime C prime D, I5 is D, so we get A B prime C D, I0 and I6 both are D prime, so we get A prime B prime C prime D prime plus ABC bar D bar. That's the Boolean function of the expression implemented by the second set of inputs. Problem 4.35. Implement the following Boolean function with a 4:1 multiplexer and external gates. First function is sum of minterms 1, 3, 4, 11, 12, 13, 14, 15. And they have given a clue, they have given hints on how to do this, but I'll give you the method straight up, so you don't need any hints. We'll use A and B as the select lines. Of course, you could use C and D as the select lines, A and C as the select lines. It's up to you. You will be able to construct a circuit. Just standard procedure. We'll use the MSB. Two most significant bits as the select lines. A and B are the select lines, so F1 is the following function. If we write out the minterms, A bar, B bar, C bar, D, that's minterm 1. A bar, B bar, C, D is minterm 2. A bar, B, C bar, D bar is minterm 4. 11 is A, B bar, C, D. 12 is A, B, C bar, D bar. 13 is A, B, C bar, D. 14 is A, B, C, D bar. 15 is A, B, C, D. So we'll group all those terms which have A and B in the same form. That is, we'll group all those terms which have A bar, B bar. Then we'll group the terms which have A bar, B, then AB, then AB bar. So F1 can be written as A bar, B bar into C bar D plus CD plus A bar B into C bar D bar plus AB bar into CD plus AB C bar AB into C bar D bar plus C bar D plus CD bar plus CD. Now this can be further simplified as C bar D plus CD is C bar plus C into D, which is nothing but D. C bar D bar as it is, CD as it is. Now C bar D bar plus C bar D is simply C bar into D bar plus D, which is C bar, and CD bar plus CD is simply C into D bar plus D, which is C. So you have C bar plus C, which is 1. So this turns out to be 1. Now you can easily implement the function using a 4:1 multiplexer. Where when A bar B bar D will be 1 only when A and B are 0, all these terms will be 0. only a bar b bar d term will be left. So the function is equal to d when a and b are 0. In the multiplexer, when a and b are 0, multiplexer selects the first input line. So we must give a d to the first input line. When a bar b is 0 1, when a and b is 0 1, all these terms will become 0. Only a bar b, c bar d bar will be left, and a bar b will be equal to 1 when a and b are 0 1. So f will be equal to c bar d bar. Similarly, in the multiplexer, when a and b are 0 and 1, it will select the line, input line I1. So you must give c bar d bar to this input line. So use an AND gate to give c bar d bar. Similarly, for I2, you will have to give cd, and I3 just give a 1. So that is how you can implement AB, f of ABCD using some external gates and a 4:1 multiplexer. Part B follows similar to part A. F2 can be written as the following Boolean expression. And we do the grouping in the following way. C bar D plus CD will reduce to, okay, we can't reduce it further, it's simply C XOR D. C bar D plus CD is nothing but C bar plus C into D, which is nothing but D. From the first two terms, you can take out D bar common, you will end up with D bar itself. And you will end up with D bar plus CD. You can use distributive law to write it as D bar plus C into D bar plus D, which will become D bar plus C. Final term will become simply D. Again, we use a 4:1 mux, two select lines, four input lines. Select lines are connected to A and B. I0 is C XOR D. I1 is D itself. Similarly, I3 is also D. I2 is D bar plus C. That will give you F2. The rest of the problems in chapter 4 are all HDL based from what I can see. I won't be solving any questions based on Verilog or HDL. I won't be solving any design based questions. If you are interested, you can look them up yourself. If you are going into the VLSI field, logic design, you want to use, you want to learn Verilog or VHDL, then you can solve problems from solve the remaining problems from problem 4.36 to 4.65. They're all such problems, so that's almost 30 problems. That's exactly 30 problems. Now we will move on to chapter 5. I will only cover up to chapter 7, 5, 6, and 7. So we'll see how many problems we can do. I think I took more sessions on chapter 4 than the previous chapters, chapter 3 and 2. Chapter 5 will also require more sessions because it is more important. Alright, let us go to a new chapter. Chapter 5 synchronous sequential logic. The D latch of figure 5.6 is constructed with 4 NAND gates and an inverter. Use NOR gates for the SR latch part and AND gates for the other two. Let me get figure 5.6 first. That is figure 5.6. They want us to use NOR gates for the SR latch part. The SR latch part is the part I circled just now. So they want us to use NOR gates instead of AND gates. Right? Let's draw that. We are using AND gates for the first part. So when we use AND gates, if enable is 0, the output of the AND gates will be 0. If output of the AND gates is 0 and we connect that to the SR latch, the next part, and obviously the output of the SR latch will remain unchanged. So the next state of Q is still no change. Now let us assume enable is 1. When enable is 1, D and D bar are passed on as inputs to the next stage. So here you will get D, here you will get D bar. and D is 0, you'll get 0 here, 1 here. They're asking us to use a NOR gate as a latch instead of NAND gate as a latch. So now what will happen, since this is 1, the output of this NOR gate will always be 0, and since that is 0, the output of this NOR gate will be 1. So we actually have the complement of D as the output there, and D is coming as this particular output, the second output. Similarly, if enable is 1 and D is 1, this is 1, this is D bar 0. Since this is 1, this output will be 0 and this output will be 1. So this is your output. For a D latch, Q should go to 0 when D is 0. So when D is 0, this is 0 and this is 1. So this, and when D is 1, Q should go to 1. So this is our Q output, this is the Q complement output. Notice that when you use NAND gates only, the upper output was the desired output Q and the lower output was Q complement. Now it has changed. If you don't want to do it that way, then you can simply put a NOT gate here and give D bar here and remove this NOT gate. Then if you replace this with NOR gates and this with AND gates, you'll get Q here and Q bar here. But with the same configuration as before, if you only change the gates, then Q and Q bar are flipped. That was part A. Part B is use NOR gates for all 4 gates. Part B. Now let us see, when enable is 0, we want the inputs to the SR latch part to be 0 0. Does that happen? It doesn't happen here. When enable is 0, this output is this D bar and this output is D. We don't want that to happen. When enable is 1, this output is 0 and this is 0. We want the opposite to happen, so now we'll have to introduce a NOT gate in between. Now what will happen if enable is 1, this is 0, so this will be D bar and this will be D. When enable is 1, this will be 0 and this will be 0, so the output states won't change. If the inputs to the SR latch part is 0 0, the outputs of the SR latch won't change. Alright, now suppose it is enabled, you're getting D bar and D. So I explained it in part A. Here, if you had given D bar and when it enable is 1, you would have received D bar here, then this would have been your Q. So now Q and Q bar are back to their original positions. This is Q and this is Q complement. All right. In part C, they want us to use only NAND gates. So they want us to remove this inverter. Why is that inverter present? It's because you want D bar here and D here. Sorry, you want D here and D bar here whenever enable is high. When enable is 0, obviously the output of the NAND gates will be 1, because if any of the inputs is 0, output of the NAND gate is 1. So that doesn't matter to us. What matters is if enable is 1, in which situation you want D bar here and D here. What you can do instead of using this NOT gate here is keep everything the same. We have assumed that enable is 1, so both these are 1. So what you get here is D bar. What you need here is D. Suppose you take this D bar and give it as the input of this NAND gate. We'll get D bar and 1 whole bar, which is nothing but D. So you can remove the NOT gate there and connect the output of the first NAND gate as one of the inputs to the second NAND gate. Alright, that's the end of this session. We started off with chapter 5. We covered only one problem. We'll solve the remaining problems in the coming sessions.